This lesson is for section 8.1, trig functions of real numbers. We do have two main objectives for the day, and that's to use our remaining Pythagorean identities, which we'll show in just a second, to simplify some trig expressions. Okay, that's our first objective. And then we're also going to learn and prove our opposite angle identities, and we'll use those to calculate values of trig functions as well. Up first, though, we actually will be taking a look at our trig functions in terms of real numbers as opposed to angle measures. So it's a very subtle difference what we're going to do here in the beginning of this lesson. But basically, prior to this chapter, our inputs have always been angle measures, right? In terms of either radians or in degrees. Now, though, we're going to change those inputs to real numbers. Our outputs will still stay, real numbers, but our inputs will change and become real numbers as well. So to change our inputs from angle measures into real numbers, what we actually want to look at is how we define a radian measure. So our radian measure, if you recall from our first section in chapter 7, was defined as S over R, or the arc length over the radius. It's the ratio of the arc length over the radius of a circle. So in this case, theta here in radians is going to be 6 centimeters over 3 centimeters. So you need to have the same linear units because these will cancel. This will leave me with 2, and we call those radians. Okay, so they are dimensionless, but we call them title of radians. Now if we look at a unit circle, things slightly change for us. So in a unit circle where the radius is 1, if we define our radian measure here as S over R, this becomes S over 1, or simply S. So theta here, that radian measure, is actually equal to its arc length. So here, in a unit circle, the radian measure of an angle actually equals the measure of the intercepted arc, so the arc length here. So you can see that I've changed the notation slightly. We're going to use t now instead of theta, but here, if this radian measure here is t radians, well, we have an arc length of t units as well. So these are equivalent to each other. Theta is now equal to its arc length. So that's how we can now use real numbers, okay, as opposed to angle measures now. We're going to use this number, which represents the arc length for that intercepted arc. Alright, so here I've got a summary of our trig functions in terms of real numbers. So now we're defining these trig functions in terms of real numbers. Our inputs have changed. So 1, obviously the notation has changed. Instead of seeing cosine of theta, you now see cosine of t. So that is a difference. It's not a major difference. It's very subtle. So you might be thinking to yourself, like, why are we doing this at all when all of these still remain the same as what we've looked at before? Well, the big difference here is that now our input can be a real number. It's the arc measure, not the radian measure anymore, okay? So it is a real number now. So the consequences of these definitions here still remains the same, where we're going to see the secant of t is equal to 1 over the cosine of t, in other words, 1 over x. So we still get the exact same, definitions here, but again, it's subtle, but it is a very important difference. Now our input here is a real number. Okay. Now, next up, we're going to talk about our Pythagorean identities. So we began with sine squared theta plus cosine squared theta equals 1. That was our first and only Pythagorean identity that we've come up with so far, and that related to our equation for our unit circle x squared plus y squared equals 1. Remember, we just substituted in values for x as the cosine of theta, and the value for y here is the sine of theta, and we arrived at our new Pythagorean identity. Well, from here, I can manipulate this even further to create 2 more unique identities. So what we're first going to do is divide both sides of our equation here by cosine squared theta. So if we divide everything here on the left side by cosine squared theta, I'm going to write that under each term here. I can simplify both the left and the right hand side here. Now on the left hand side, sine squared theta over cosine squared theta becomes tangent squared theta. Cosine squared theta over cosine squared theta is simply 1. And 1 over cosine squared theta gives me secant squared theta. So this is a new Pythagorean identity. It is unique, and you're going to use that now when you prove trig identities. Now our next trig identity comes from taking our original Pythagorean identity here and manipulating it, but instead of dividing by cosine squared, we're going to divide by sine squared theta on both sides. So if I write sine squared theta under each term, you can simplify this really easily. and arrive at our new identity. So here, sine squared theta over sine squared theta is 1. We end up with 1 plus cosine squared theta over sine squared theta is going to be giving me cotangent squared theta. And 1 over sine squared theta is cosecant squared theta. So here is my third Pythagorean identity. Now these are identities that you're going to use throughout the next few chapters, and it just increases your ability now to simplify and prove trig identities and manipulate equations to your benefit. So in problem 1, we're actually going to be practicing a technique that you're going to be using next year in BC Calc. So in order to simplify this expression here, what we can do is actually use substitution of a trig function in for our variable here so that we can rewrite the denominator as a perfect square. So right now I can't take the square root of this inside here. U squared minus 1 is simply the difference of squares. I can't square root this. However, if I turn that into a perfect square, then I can manage to square root that and further simplify. So I can rationalize the denominator. So this is again a technique that's useful in BC Calc. So let's begin by substituting in u is equal to secant theta. So we have secant theta over the square root of secant squared theta minus 1. Now this I can use substitution again for, because I know that by my third trig identity we just talked about, tangent squared theta plus 1 is equal to secant squared theta. So now this is equivalent to saying secant theta over the square root of tangent squared theta. Now this, if I want to take the square root of this, this is simply going to be the absolute value of the tangent of theta. Now because theta lies between 0 and half pi, I know that this tangent of theta will always be positive. So secant theta over tan theta is what this simplifies to. It's positive tan theta. And now, if I simplify here, I have 1 over cosine theta divided by sine theta over cosine theta. So canceling here, if I just rewrite this a little bit easier for you to see, my cosine thetas will cancel, and I'm left with 1 over sine theta or cosecant theta. So by substitution, I can simplify this entire expression here and use a technique, again, that's useful in BC Calc. So we're just going to practice a couple problems like this in your homework, where you're just going to be substituting in a trig function for a real number. Okay, next up, number 2 asks us to simplify this trig expression. Now this is something that you've already done a lot of in chapter 7, but now because we know more identities, we can continue to use new techniques and continue to prove trig identities as well as just simplify trig expressions. So the first thing I want to do when I look at this is look at my numerator, and I notice that I have secant of t in both of these terms here, so I'm going to factor that out so that I have secant of t multiplied by 1 plus tan squared t. In my denominator, you may actually see this as a difference of squares. So if I did that, I'd have cotangent of t plus cosecant of t and cotangent of t minus cosecant of t. So that might be your first instinct here, just because you see a difference of squares. But in fact, this is really actually an alteration of our trig identity that we just talked about above. Cotangent squared theta plus 1 equals cosecant squared theta. So in this case, it would not be useful for me to rewrite that and factor this as from the difference of squares here. Instead, I'm going to use some substitution. So cotangent squared t minus cosecant squared t. Let's try to manipulate this identity here. If I subtract cosecant squared over to this side and the 1 over to here, I'm left with cotangent squared theta minus cosecant squared theta equaling negative 1, which means that this denominator here is actually just equal to negative 1. So I'm going to use substitution here, and that value is just negative 1. Now in the numerator, 1 plus tangent squared t was also something that we just looked at. Remember, tangent squared theta plus 1 was equal to secant squared theta. So I'm going to use substitution here, call that secant squared theta now, so that I probably shouldn't have just crossed that out, sorry. I'm going to use substitution and say secant t times secant squared t divided by negative 1 is the equivalent to this expression here. And simplifying now, I have negative secant cubed t. Alright, so again, we're just going to continue to use new identities and try to recognize any alteration of those said identities. Alright, let's do a little bit of review about whether a function is even or odd. So if for all t, in the domain of f, we have f of negative t equal to f of t, then we say that that function is an even function. So if for all t in the domain of f, f of negative t is equal to f of t, this is symmetric then about the y-axis. So like here we have this quadratic function where clearly any point xy on this parabola can be reflected here over the y-axis so that we have negative x comma y. So again, for all t in the domain of f, you can also write this as f of negative x is equal to f of x. Okay, f of negative x is equal to y, which is also equal to f of x. Now for an odd function, for all the domain for all t in the domain of f, we have f of negative t equals the opposite of f of t. So for example here we have x comma y, and here in my odd function, which is symmetric about the origin, I have the coordinate negative x, negative y. Okay, so for all t in the domain of f, we have f of negative t equaling negative f of t. So we're talking about even and odd functions because we end up, when we talk about trig functions, these opposite angle identities, which are helpful to understand in terms of whether they're even or odd. So we see these three identities, which we'll prove in just a second, but just to introduce them to you, the cosine of negative t is equal to the cosine of t. So in other words, cosine is an even function, so cosine graph should be symmetric about the y-axis. Now, sine of negative t is equal to the opposite of sine of t, making sine an odd function, so the graph of the sine function here is going to be symmetric about the origin. And our last opposite angle identity states that the tangent of negative t is equal to the opposite of tangent of t. In other words, tangent is also an odd function. Alright, we can actually prove these opposite angle identities by first just creating a little sketch of the unit circle and creating theta on this unit circle. So let's see, let's draw in an angle, measure theta, radians. Okay, so let's look at theta now. The coordinate here where theta intersects that unit circle would be the coordinate x, y. Let's just call it xy. But in terms of, our trig function values here, this would be cosine of theta, comma sine of theta. Okay. Now I'm also going to create negative theta. So here's an angle measure of negative theta radians. So this coordinate here, let's call it P prime. This is simply this point reflected over the y-axis, making this coordinate x, comma, negative y. And if we want to define it in terms of sine and cosine, this would be the sine of negative theta. Oh, I'm sorry, cosine of negative theta, my bad. So the cosine of negative theta and the sine of negative theta. Okay? Now, based off of this idea, though, okay, that we've just reflected this coordinate, well, I could rewrite that alternatively, this point here, as this reflected, right? So that would still be the cosine of theta, comma, this coordinate here reflected ends up changing to the opposite of the sine of theta. Okay, so again, I'm just rewriting this coordinate alternatively by reflecting this point here. Now we see that since these are equivalent expressions of the exact same point, right, the cosine of negative theta is equal to the cosine of theta, and the sine of negative theta is equal to the opposite of sine of theta. So here are the first two of our opposite angle identities. So our third identity here, let's move this up a little bit. Our third identity comes from actually starting with just the tangent of negative theta. Okay, so we can't see what the tangent of negative theta is just by looking at our diagram, but let's just use our definitions of, what tangent is. So tangent is the ratio of sine over cosine, so this would be sine of negative theta over the cosine of negative theta. Now we just defined that the sine of negative theta was actually equal to, right above here, the opposite of sine of positive theta over, if I want to rewrite the cosine of negative theta, that's actually equal to, in our identity above, just the cosine of positive theta. And if we simplify this, this is simply a tangent ratio, so the opposite of the tangent of positive theta here. So if we want to simplify even more, write it a little bit more explicitly, the tangent of negative theta is equal to the opposite of the tangent of positive theta. So there is our third opposite angle identity. Alright, so let's use these opposite angle identities here. In question 3 it says that the cosine of m is equal to negative 0.45, and we're supposed to find the cosine of the opposite of m. So we just talked about it, but the cosine of m should equal the cosine of the opposite of m. So in this case, negative 0.45, right, is equal to the cosine of m, should also equal the cosine of negative m. So negative 0.45 is my answer for number 3. And number 4, the tangent of p is equal to 1.2, and we're supposed to find the tangent of the opposite of p. Remember that the tangent of opposite of p is equal to the negative, or the opposite of just tangent of p. So in this case, since the tangent of p is 1.2, let's just use substitution. We have the opposite of 1.2 is equal to the tangent of negative p. So again, I'm just using this here and substituting in 1.2. In number 5, so that's the answer for number 4. In number 5, it says if the cosine of g is equal to 0.36, find the cosine squared of negative g plus the sine squared of negative g, or opposite of g. Now, sometimes you can overthink these, and you might start plugging in some values here. But this just goes back to one of our first identities that we learned, that cosine squared plus sine squared is equal to 1. So no matter what I have here, right, it's equal to 1. Now, if that seems tough for you to remember these opposite angle identities, don't freak out about it, because even I don't really have them memorized, I guess, because all I do is think in my head, what that unit circle here looks like. So I draw in theta here, and negative theta. And then I think, okay, here's the coordinate x, y. Reflected, it would be x, negative y. And this is the cosine of negative theta and the sine of negative theta. But if I look at cosine theta and sine theta here, and I reflect those coordinates, well, then I end up with an alternative way of writing that as cosine of theta and the opposite of sine of theta, right? Just using the idea that this is just x, negative y. So these values here, in other words, sine of negative theta is equal to the opposite of sine theta, and the cosine of negative theta is equal to cosine of theta. And a lot of times you don't even need to write all that out. You can just think in your head what happens to x, and y when you reflect it over the x-axis. So very basic, right, in terms of just thinking of it as a picture. Okay, so the last part of our lesson here is going to be a discussion about periodic functions. So I think you might have already talked a little bit about it, maybe in physics, like waves. But basically, the reason why we're starting this is because tomorrow you're going to start graphing the sine and cosine functions, and it's helpful to know that they're periodic functions. So a periodic function is just a function where its values are repeated in regular intervals or periods. So here you can see it graphically really easily in this graph of f of x here. After I go a distance, or in time interval of p units, well, I see that same shape and the same values here repeated again and again and again. So this represents a periodic function. The next topic here, periodicity. Ugh, I hate that word. I don't think I say it right at all. Periodicity, whatever. But basically, for a sine and cosine function here, every 2 pi represents a complete trip around your unit circle. So the cosine of t would be equivalent to the cosine of t plus 2 pi k, where k here represents 1 trip around the circle. So in other words, 1 revolution. And that's, again, because in a unit circle, our circumference of that unit circle is 2 pi, right? 2 pi r would be normally our circumference, but because it's a unit circle, radius of 1, my circumference here is 2 pi. So if I travel 2 pi around the circle at any point, let's say I start here, and I travel 2 pi, I'm right back here at point P. Okay? So that's really all that this is saying, is that the value here at any time, or any value, real number of t, that if you add, however many trips around the circle, but in an interval of 2 pi times that trip, you end up right back to where you started. Okay? So that is helpful now in doing some further trig values. For number 6, what I'm going to do is rewrite this as the cosine, so negative 19 pi here. Let's rewrite that as the cosine of pi minus 20 pi, right? This would be equivalent to negative 19 pi. Now what this is saying here is that if I started at the cosine of pi here, so if I started at pi radians, and I go around the circle here, negative 20 pi, well that's going in a clockwise direction, right? So that would be going in this direction here. So I'm starting here and I'm going this way. Well, I would make 10 revolutions around my unit circle and I end up right back here, right? Right back there. That would signify going negative 20 pi, a distance of negative 20 pi around this unit circle. Well, really then all I'm calculating is the cosine of pi. So this really is irrelevant. I'm just going to calculate the cosine of pi. The cosine of pi, we know that this coordinate is negative 1, 0. The cosine of pi is negative 1. Now, when I look at the sine of 5 halves pi, I want to rewrite that. So 5 halves pi as the sine of pi over 2 plus 2 pi. So again, I'm starting at, let's use that same diagram here. Let's start at pi over 2, this coordinate here. And this time we're going to add, so we're going in the, But yeah, this clockwise. No, this is counterclockwise. God, I can't even keep my clock right. Okay, so counterclockwise would be going in the positive direction. So I go around this 2 pi, right, distance of 2 pi, and I end up right back here. Again, this is totally irrelevant. So really, when I'm looking at the sine of 5 halves pi, that is simply the sine of pi over 2. Okay, so the sine of pi over 2, this coordinate here is 0, 1, and the sine of pi over 2 is the y value, which is 1. Alrighty, that's the end of the lesson. Nice job. I'll see you guys tomorrow.